bits. Let's see what it's asking us. All right. So we're given an arbitrary 32-bit integer, n. So 32-bit, we sort of talked about that last time. Basically means in its binary representation, it's going to have 32 bits, zeros and ones, or zeros or ones, I should say. Anyway, point is, we're given one of these 32-bit integers. We want to take its binary representation. We want to split the bits into pairs and then swap each pair. So basically, they give us an illustration of that over here. We've got the number 13. They're saying the answer should be 14. Let's find out why. So 13 can be represented in binary as 1101. If we split it into pairs, the first pair is the 1, 1 over here. When we swap that, if we switch the order of these, it doesn't make a difference, still just 1, 1. But the other one, 0, 1, when we swap that one, it becomes 1, 0. So it actually does make a difference there. Not much of a difference, but enough to bump it up from 13 to 14 in this case. In the other example, it makes a bit more of a difference. So like we start with this 74 over here, we put that into binary, split it up into pairs, and then we flip each pair of bits, we swap them, and it ends up being a totally different number. So I wonder, could the number get smaller this way? I guess it could, right? Like if it started with a 1, 0 instead of a 0, 1, and that'd make it smaller. So, okay, I guess it's hard to predict what kind of correlation there's going to be between these kinds of numbers. It might be bigger, it might be smaller, it might be really close to the original. I suppose it could be the same, like if it was all ones or all zeros. Anyway, point is, okay, one thing to notice here, these numbers, we sort of need for them to be even. So normally if we were to convert 74 to binary, it probably wouldn't have this 0 out in front over here. So that's something worth considering. We might want to think about that for later on when we're actually coming out with the algorithm. Anyway, what else? Is there anything else to note here? Okay, I think that's about it. I mean, in terms of our guaranteed constraints, it doesn't go quite all the way to 32, but pretty close. Okay, so I guess we might as well get started now. Normally, the way we've been doing these, we start with like a n.toString with an argument of 2, just converting it into a binary number, a binary string. So yeah, we'll probably do something like that, at least for the first attempt. Now, in some of these, we've also been going a step further, converting to an array so that we can do like a reduce on that or something like that. In this case, we're not going to go quite that far. We're going to be just converting it to a string. And that's sort of the same as what we did last time for, what number would it have been? 21? Yeah, 21. The second rightmost 0-bit one. We ended up starting that one, at least, with a regular expression, actually. So I think we could probably do the same sort of thing for this one. I think we could probably use a regular expression just to break up the number, to break it up into pairs that we can deal with on their own. So let's maybe try that. So what regular expression can we use? Well, basically something that's going to be sort of like this, right? We're going to have a 0 or a 1. So, anyway, the point is these are our options, right? So we're saying with this, it could be a 0, it could be a 1. And we're going to have more than one of these, right? Specifically, if it's a pair, we're going to have 2 of these. So we'll have something like this. And this doesn't necessarily mean we're going to have 2 zeros or 2 1s. It could be a 0, 1 or a 1, 0. So this should cover all the bases for the kinds of pairs that we could have in here. Okay, so what do we want to do with this? I guess we'll do like an n.toString with the 2, of course, that it's binary. And we'll just do a match on this. Do I have the order right on that one? Yeah, okay. So in this case, we're saying 1, 1, which, okay, makes sense. That's like the first pair over here, but that's not all of them, right? We want not just the first one, but all of them. So we'll put the global flag on the end here. We'll put the little G, and that's going to tell us, I don't want just the first instance, the first match of this thing. I want every single one of them you can possibly give me. Well, actually, that's not quite true. Another thing to notice about like this match, and if we were to use this for other methods and stuff like that, the way this regular expression is going to work in terms of the G here is it's not going to overlap itself. So like That's actually very good for our purposes, right? It's looking for pairs of zeros and ones. It's looking for binary pairs, basically, right? So it's going to return that one. It's going to return this one over here. So the 1, 1 and the 0, 1. That's what we've got. But notice it's not giving us like the 1, 0. And it's because it doesn't overlap. So it's breaking it up exactly the way we want it to, right into pairs. So nice. Okay, that's good stuff. So that's probably the regular expression we want to use. But we don't want to just do a match on this. What we actually want to do is we want to take this string and we want to do some replacements. We want to replace these matches with something else, right? I mean, the idea is that everything that this matches up with, we want to replace with the swapped version, right? Where we swap the first and second characters. So let's do that. Basically, the idea is that over here, we're going to get some kind of pair, right? So, okay, sorry, I'll step back a sec to address what this replace is doing. So the replace, it's a string built-in method. So we do dot replace, and then this can take in a variety of things. Like we can have a string for the first argument and a string for the second argument. Like for example, maybe we make this the string that's just the number 0, and then we make this the string that's the number 1. That would just replace a 0 with a 1. It would replace the first one. If we wanted to replace all of them, that's when we need to use something like a globally flagged regular expression like what we have over here. So as far as I know, that's the only way to do a replace all without doing like a loop, putting it into a while loop or something like that. Anyway, okay, so we got this. It's working the way we want. In terms of how we're going to match it, we're using this regular expression so that it matches all of these pairs. But then what are we going to do with it? Well, normally we could put something in here, like we could put this in and it's just going to replace them with a 1. That's not what we want. What we want is something that's just it's going to give us something different depending on what we start with here, right? So if we start with the pair 0, 1, we want to return 1, 0. So it's going to depend on the input. So what we can do is put a function in here. We could write it out like this, or we could use an arrow function. So a function that takes in a pair, and then it's going to return something like pair at 1 plus pair at 0. It's just going to flip them, right? It's just going to, switch them around. So let's try running this. We'll see what we get from that. Well, that's pretty good, I think, right? We got 1, 1, 1, 0. That's what we want for this first one. So for that one anyway, looks like this is working pretty good. Now, it's getting a bit unruly in here, so I'm just going to try to cut down the size of this thing. So for now, I'll just make it an arrow function, so I don't need to put the return or anything like that. We could, if we wanted to, we could shorten this down to like a single character name, but this is probably fine. And keep in mind, we're reversing the pair here, and we could do something like, like pair, pair dot, or I guess we need to put it into an array, but something like this, like a dot reverse and then a dot join. We could do something like that. I think that would work just as well here. Let's see. Yeah, produces the same thing. So that would work, but it's kind of overkill. It's more than we require because we know that these are going to be just 2 characters long. And so we can just put the second character first and the first character last. We can just do it directly. Not a problem. Okay, cool. So that's good, but it's not a number yet. So we're going to parse int this thing. We're going to parse int around it. And remember, since it's a binary string, we don't want it to say, oh yeah, like 1110, right? Which is what it would normally do if I just let it go like this. Instead, we want to be using a second argument for the parse int. So we'll just put a little comma in here to delineate the 2 arguments. And then for the second one, since we want it to be base 2 instead of base 10, like the way it's interpreting it now, we're going to put in a 2 over here. So we'll run this. And okay, so it's passing half of the test, including the first one over here. So it's getting the 14, so that's good. But what's going on with this one? This one's not working out. We're getting 52 when we should be getting 133. well, it's a really different value. So what's going on with that? Let's try to find out. So I wonder if maybe we should just turn off the parse int for now and take a look at test2 without it to see what it's looking like in binary. Okay, there we go. So this is what we want it to be. This is what we're getting instead. And if we take a look, it's because, you remember how we said we need the 0 in front here? Well, we're not starting with that 0 in front. So basically instead, we're just getting 1, 0. We flip that, so we get 0, 1. And then we start with another 0, 1, 1, and we flip that to be a 1, 0. And then another 0, 1, so that's a 1, 0. And then the 0 at the end stays the same. It's not part of a pair, so it's not going to get replaced. So we get this weird kind of number, which I guess ended up being 52. So it's not quite what we want. We need some way of getting the 0 in front when we need it. So, okay. There probably are a few ways we could do that. I'm sure there's like a really, really easy way of doing it, but not one that I've thought of. Normally what I would do in a case like this, if we were allowed to use more than one line, you might have noticed at the start this is one of those one-liners. We just need to return just a single thing. I'm pretty sure anyway. Anyway, the point is, so because of that, we can't really do this, but what I would normally do is probably something like this, right? Have a padding function that would basically start with, what would we want? I guess it would take in a string, and let's just make this one specific to this case. So it would say, I guess we need a 32-bit integer, right? So it would just return something like, we do something like this, where we have a 0.repeat 32 minus string.length, right? And then plus string. There we go. So something like that would work. This would be a padding function. I think it would work anyway. So it would basically put all the missing zeros in front of it so that it would make this into a 32 length string, basically. A 32-bit binary string. That's what it would be. And we'd start with a bunch of zeros, probably, like most of these numbers. You know, if you were to give it this one, for example, this only has 4 significant bits over here. So if we were to put that into this padding function, it would put 28. Did I do that right? Yeah, 28 zeros right in front of this. So basically, it'd be a whole bunch of zeros followed by a 1101. It wouldn't necessarily be that way, you know, like we might have much bigger numbers in some of these other tests. Yeah, like that's a lot of ones over here. So like we probably wouldn't have many other spaces here where we put the zeros in. You know, but the point is it depends on the length of the string. So that's why it would sort of be nice if we could use a function like this here. So unfortunately, we can't quite do that because, like I said, we need to do this on, or I think, like, let's try, no, we can only change the ... and the ... is what we started with. It's kind of funny. It sort of looks like a little emoji here, you know, this guy. Anyway, all right. Sorry, just noticed that. Going back to this, let's get rid of the padding function for now, or maybe for now, let's like cut it out and put it into a comment below here. Yeah, okay, that's that works, I think. Does that work? No, it doesn't like that. All right, I'll paste it somewhere off screen and then we'll bring it back later. So there we go. Okay. All right, sorry about that. So getting back to this thing over here, the problem is that we need to do this all in one line, and we need to sort of be able to tell how many zeros we want to put onto the beginning here. Right from the start sort of thing. So here, we'll put 0.repeat, and we're going to have some number in there, and then so basically this is going to be some number of zeros that we're going to use for the padding, and we're going to add that on to, we're going to concatenate that with the n.toString 2 here. So that's the binary representation of n as a string. And I might as well just put these in parentheses over here so that basically all of this is going to be treated as one string, which is going to have the replace done to it afterwards. Okay, cool. So what are we going to have from here? Well, we need to decide how many zeros we're going to put in. So we're going to have this repeat thing. And how many is it going to be? Well, earlier we had 32 minus str.length. But what's str? Well, basically we were putting in as an input this thing, right? Like our binary representation. So we can just put that in for now. Try running that. And will that work? Will that give us sort of the types of numbers that we're looking for anyway? And keep in mind, for now, it might not look like exactly what we're looking for because it's going to be a string. It's not going to be represented as a number. So yeah, I think that's probably 32, like a length of 32. We could measure it, I guess, but you know, I have faith. Anyway, that looks like the answer we're looking for, right? If we take a look at this one over here, yeah, that looks like this one over here. And you might be wondering, like, well, is it okay that we're making it so long? Like, does it need to be that long? And the answer is no, it doesn't need to be this long. It just needs to be an even number, an even length, and maybe we'll talk about that in just a little while. But is it going to make a difference if it's this long? Like, is it going to mess with it at all? And the answer is no, because over here, like all these extra pairs of zeros, well, they're just going to get flipped and they're going to still be pairs of zeros, you know? Like 0, 0 gets flipped and it's still 0, 0. So it's not really going to make much of a difference. Okay, so I think we have probably the numbers we're looking for. Yeah, it looks that way so far. We just need to do our parseInt on this, and keep in mind, gotta have that extra argument of 2 because we're talking about a binary number. And there we go. Okay, so is that gonna pass all the hiddens? Let's try it. Ooh, it does. Okay, great. We got 100 experience for that. And we're 75% of the way through. We're 3/4 of the way through. So that's pretty good. All right, cool. Yeah, that's weird. Doesn't it normally open the solutions after you do this? Okay, well, anyway. All right, so what do we want to change about this thing? Well, okay, I have a couple issues with it. There are a few changes that I want to make, but let's see, where to start? I guess probably, okay, to me the biggest issue, okay, I was just thinking about it. All right, let's go back over here. To me, the biggest issue right now is the fact that we have an n.toString 2 and then another n.toString 2. So obviously, normally, if I were dealing with something like this, I would put in a variable, you know, I'd say that like, I don't know, S is, or B for binary, for example, is assign the value of this thing. And technically we could do that, right? Like we could say B is this thing, put in parentheses, and then the next time we need to use it, we can just put that in there. Is it going to work if we do that? Yeah, it's going to work, but it's kind of inelegant. I mean, I don't really like the idea that this doesn't have like a let or a const or a var in front of it. It's just kind of, it's not really, it doesn't seem all that declarative. Anyway, the point is, so yeah, normally I would use a variable. I don't really want to do that in line because, yeah, it's kind of ugly. Anyway, the point is, how are we going to deal with that? Well, there are two ways. At least two ways I was able to think of that we could deal with this. One way would be to actually use that function that we had before. So I pasted it in off screen. Let's get it back in here so we can take a look at it. So here we go. We've got this padding function. Basically, it takes in a string and it just does, well, essentially what we have over here, right? So we want to basically take this function and actually put it in line here, actually call it like right here. So we could do that. Basically, let me just cut down the size of the function first. So instead of having like the word function and all that, we'll just use an arrow function. So normally I would probably put like a var or something like that in front, but we're not really going to be able to do that for this one. So we'll just we'll do something like this. Okay, so yeah, that's basically it. I mean, this is essentially what our padding function is doing, right? So we want to take this function and we want to call it. So we have something like this, and we normally want to call it like pad with n.toString 2, right? That's sort of normally what we would do. We would call this, and then we would do the dot replace and all of that on this thing. That's sort of the idea. Now, in this case, all of this is our padding function, right? So we technically don't really need to separate these two things, right? Like we're defining pad over here as being this function. We're calling pad over here, but we could just take this thing, the calling part of this, and just stick it right on the end over there, and then it's gonna declare and call this function at the same time with this input. It's going to return that, and then we're going to be able to do the replace and all that stuff on this. At least that's the plan. We'll see how it works. So let's try pasting that in. Let's try running that. And oh, yeah. There's extra space over here. It doesn't like that. So let's try running that. And uh-oh, we got an issue. So what's the issue here? Is it wrong number of parentheses or something like that? Let's see. This matches up. And that matches up, right? Doesn't that seem correct? Maybe we need another set around here. Is that the issue? No, that doesn't seem to be the issue. Okay, let's just make sure. Let's take off the replace for just a sec and try running that, see if that actually works or if that has an issue with it. Okay, so this is without the replace. It's doing the padding, so that part is working. It's having an issue with the replace now, though. Why is that? We paste that in. So dot replace. Do I have like too many? Oh yeah. Okay, so I have too many parentheses now. Why is that? Oh, because I don't have the parse int on it yet. Oh my god. All right. So yeah, we can just delete that part. Jeez. What a silly thing. Anyway, okay, there we go. Great. Let's get the parse int on here. Let's try that. And we'll run that, and great. Cool, I feel a little better about that. I think it's a bit nicer than we're not actually repeating this thing. We're not using like an inline variable declaration and assignment, although technically we are. Because we've got this thing over here. We've got pad is assigned the value of str. But the thing is, keep in mind, the reason we're calling this pad before, the reason this function had a name before is because we were invoking the function by that name. We had to call it. And so basically, we needed for it to have a name so that it could be called. But the thing is, we're calling it right now. So do we really need for it to have a name? Could we just have this anonymous function in here that we're just calling with this input? And let me get those on the same line over here so that, oh, there we go. Okay. So yeah, basically the idea is that we've got this function here and we're calling it with this input that's toString 2. Okay, so let's run the test on that. Okay, cool. So that's working. I think that's a little better. Yeah, I like this better. I think it's nicer. So let's just make sure it's passing all the hiddens. And we got a question from Rainbow Sparkles. Whatever happened to the mirror bits task? Mirror bits, that was number 20. Yeah, we did that one, right? Did I not put that one on YouTube yet? I thought I put it up. Is it not up there yet? I was pretty sure I meant to put it up last night anyway. Anyway, as for now, what have we got over here? Now, we said there are going to be two ways of doing this, right? We said that we would resolve the issue of having the toString in there 2 times. We said that there'd be 2 ways of doing that. So one way was to put in this function over here. I think that's pretty neat. It's passing all the tests. Whoops. It's passing all the tests. It's doing what we want it to do. But we could do it in another way. So we're going to copy this, and here we go. We'll put the 1 in front of that one so that it doesn't call that one anymore. And let's look at this a little differently. So we don't need, my claim is we're not going to need this function over here. So we're going to have, maybe we should take off the parse int for now just to sort of simplify things. Yeah, that's probably a good idea. Okay, so Where's this one beginning? There we go. And then we're calling it with that. Yeah, okay, so I don't exactly want to call it with that. I do want to just add that in. So is that the right number, parentheses? Yeah, that looks good. Okay, and then we don't have str.length. So instead of doing this str.length thing, we're going to do something a little bit different for this. So instead, we're going to use just math. We're going to do a math trick to find out the length of this thing. Because, I mean, the length of this thing is basically going to be like, I guess the highest bit, right? It's going to be like the index of the highest set bit over here. So we could probably figure that out by using a logarithm, because this has to do with powers of 2, right? Like, which is the highest power of 2 that this thing would be divisible by. So that's a log situation. So we'll use a logarithm on this thing. We're going to do math.log2. So this is an ES6 thing. This is nice. They built this one in for us. Before, we would have had to just do like math.log of whatever the argument is divided by math.log of 2. That's the change of base trick. But we don't have to do that anymore for a couple of these special ones. So we've got log 2, we've got log 10. Can we do it without converting to a string? Maybe. We'll find out later. We'll maybe get to that. We'll try it anyway. We'll see. As for now, math.log2 of what? Of n. Okay, so math.log2 of n. And then that's going to give us like a decimal number, most likely, depending on the input. So we should probably do like a math.floor, or technically what we actually want to do in this case is more like a math.ceil. We want to actually round this up, because if we were to take, for example, okay, wait, is that? Yeah, I think that's close to the way we want it to be. Like if we were to take the 13, for example, so 13, what's the highest power? 2 we could divide into this thing. Well, 8 would, that this is more like that this is bigger than is what I should say. So yeah, it's bigger than 8. It's not bigger than 16. So like 3 would be the maximum. So it's probably going to be like 3.5, 3.7, something like that. So we want to actually round up, because the length of this thing is actually 4. So we're going to do a ceiling here instead of a floor. And let's try running that. Let's see if that's going to give us, okay, so it's telling us we have an invalid count value. So that's kind of weird. So it's basically telling us that this thing in here that we're getting, it's invalid. That's what it's telling us. So let's unpack this. Let's just get rid of all the stuff that isn't this, and we'll see what we get. Is that the right number of parentheses? Hopefully. Let's see if it runs. What are we actually getting from this? Well, 28. Makes sense. Like we said, we need 28 zeros in front of this thing, so no surprises there. 25 for this one. Okay, that makes sense, yeah, because this one would have a length of 7, so this looks like it's working pretty good. This one would be 2. I think this is the one that had like 31s or something like that. This one over here is giving us a null, so that's probably the problem over here. Why are we getting a null from this one? Well, technically, if we try to take a logarithm of 0, okay, if you guys remember, if we were to try to graph a logarithmic function, like if we had a log graph, then it would look something like this. It's like an exponential function reflected in the line y equals x, and so we would have like a vertical asymptote right along the y-axis. So technically we'd have like a negative infinity coming out of this thing, which is, yeah, not really a number, so I think that's why we're getting null over here. So one way we can handle this is we can put a +1 on this, and that seems like it's going to work the same way. It's conceivable the +1 is something that we actually should have had on here the whole time. I'm not sure. We'd have to look at more specific cases like right around the edges, but anyway, point is, this looks like it's working. Looks like it's giving us the right thing, right? 32 seems like a reasonable output because this has nothing, right? This would be sort of an empty thing, so we'd put a bunch of zeros in front of it. Okay, cool. So that should work. But now I need to do a bunch of undos because there's a bunch of other stuff over here. Okay, that wasn't that many. So what did we do over here? Was it just the +1? Was that the only change that we made? Let's find out. Yeah, okay, and then we need the parseInt on this thing, right? So parseInt. Okay, and 2. Is that good? That's good. Let's see if it passes all the hidden tests as well. Yeah, okay, great. We're doing great. Okay, let's see, were there any other changes we wanted to make to this? Well, I suppose there's like one other way we could deal with this that's maybe worth mentioning for now. So we were talking about this before and how putting the 32s, making it a 32-bit string, so putting, I guess I have to get rid of the parse int to see this, so yeah, let's do that. Yeah, we were saying before, like putting all those zeros in front of it, it's not going to actually affect the answer. It's still going to give us the right answer. Oh, yeah, okay, well, that's a good reminder as well. It's still going to give us the right answer, except it is like longer than we need it to be, right? It is kind of overkill, because the only thing that we really need to make sure of is that there's an even number of bits here, that there's an even number of digits. So essentially what that amounts to is if we already have an even number of bits, don't add a 0. If we have an odd number of bits here, do add a 0. And when I say add, I mean, concatenate it onto the left. But anyway, the point is, we probably don't need all 32 of these things. All we really need is maybe one of them, right? So we could do something like this. Maybe I'll model it after this one, actually. Yeah, that might be better. So, okay, great. So this one basically said we're going to have 0 how many times? 32 minus string.length times. Well, technically, couldn't we just do like string.length mod 2 times? Because if it's even, this would be a 0. If it's odd, this would be a 1. And so we'd put a 1 in front of it. Would that work? Let's find out. All these moments are so suspenseful. There we go. Okay, great. So maybe that's a little better, just because like it means we don't have to do as many of these swaps, right? We don't need to flip them around as much. So yeah, maybe that's better. I don't know, up to you. And we could modify this one over here to do the same sort of thing, because we have, like, this is giving us the length. So we could just say, like, put the 0 in if the length is even, or put the 0 in if the length is odd, and don't put it in if it's even. Anyway, something like that we could do. What else could we do with this? I guess we could take this part over here. Yeah, we could check even odd with Bitwise as well. So we would just do the and 1. Yeah, that would work for sure. So yeah, maybe that would be a little more in the spirit of these kinds of problems, eh? If we were to do it this way, just put the and 1 on the end. Yeah, that's nice, I think. Feels a little more binary. Although, again, like, to me, that's the big offender, and we will try to address that in just a sec. Before we do, there's just one more thing I wanted to maybe do here. It's for the replace, specifically this part of it. So here we're putting in a function. Now, we could just put in, like, if we were to put in, actually, for now, let's just put in a 0. Oh, I think I'm on the wrong keyboard setting here. Yeah. Okay, so if we were to just make it all zeros, everything should be returned 0 at this point, right? Yeah, get a bunch of zeros, so yeah, one of them would be right. Anyway, the point is, for this, could we do something different? Like, could we, here's what I'm wondering. If we could take an object and then return, like, oh, is that gonna work though? Okay, maybe that's not gonna work, because I basically wanted to put the match in here. Oh, well, maybe we could just do it this way. So, we could say something like this, and we'd have an object at that pair. Yeah, there we go. Yeah, I guess we could do it this way. That's a little less exciting, but yeah, we could just say something like 0, 0 is its own inversion. It's its own swapped value, right? 0, 1 goes to 1, 0, and likewise, and then 1, 1. Yeah, 1, 1, and 1, 1, just itself, right? So we could run that, and I think, oh no. What's wrong with this one? What does it not like? Did I do a mistake? what did I do? Pair. Yeah, for some reason. Oh, you know what? I think it's because. Yeah. Okay. I get this. Okay. This is a subtle thing. This really messed with me before. Okay, I'm really glad this is coming up. Okay, this is good. So, you know how there's like two ways we can do arrow functions? Like for an arrow function, we could do something where it's like, f is something that takes x to x plus 1, right? We could do something like that. Or if we wanted to, we could say x is something that goes into this other function, right? And it would look like this, right? So, and maybe we could do other stuff as well before that. Like we could say, let y be assigned the value of x plus 1, and then we would like return y. Okay, so basically, if it sees these curlies, if it sees the braces over here, then it's going to assume we're talking about this kind of way of doing it, right? It's going to assume it's looking for like a return or something like that, right? So it's looking for this kind of structure as soon as it sees these. Well, I want to use these for something totally different. I want to use these to represent an object, like a JSON, right? So this is confusing it. And what I really want is I want it to be the way it would interpret these without this, right? So if it doesn't have the braces, then it's going to interpret this as just returning whatever we see after this. So yeah, this really tripped me up before. I think if we maybe just wrap this up with some parentheses, that might actually fix the issue. Let's find out. Oh, yeah, sorry, I forgot. My mistake. Okay, let's run this. Yes, okay, there we go. So that works. Yeah, maybe that's a little better. So, okay, cool. I think that's going to pass the hiddens. Let's just run that. And we'll see what happens. Yeah, great. Okay, cool. So this is nice. We've got basically 3 working algorithms. They're all working really hard, and they're doing a great job, doing the best they can. Okay, but I want to try this in a new way. Our guy Rainbow Sprinkles in the chat made a suggestion that we should maybe try to do this without converting it to a string, and I think that's a solid suggestion. So let's try to do that. Let's try to think about this bitwise and like what we're actually trying to do here. So I want to use this one as an example, the 74 over here. So let's see, we could just try to remember this number, or maybe it'd be easier to just remember the 74. Oh, whoops, still got some stuff over here. Okay, let me clear that out, clear page. Okay, so we've got the 74, and we basically want to convert that into binary. So we've got 74, it's a decimal number, and we want to convert it into a binary number. So let's just get set up for that. Let's say, yeah, we'll switch to red, and we'll have 64, 32, 16, 8, 4, just putting our powers of 2 down so that we can construct the binary number from here. So, okay, we want to put this in a binary. So we'll say, well, does 64 fit into 74? Yeah, it does. So we'll have 164. What's going to be left? Well, 10, right? We take 64 from 74, we got 10 left. Does 32 fit? 16? No. Does 8 fit? Actually, yeah, it does. We can fit an 8 in here. What's left over? 2. So we can't fit a 4 into there. We can fit a 2, and after that, we're done. So 0 for everything that comes after that. Okay, 1, 0, 0, 1, 0, 1, 0. Does that match what we had over here? I hope it does. Yep, looks the same. Okay, cool. Great, so we've got this in binary now. Now, what do we actually want to do with this number? Well, we want the 0 in front of it, first of all. That was what we spent the past half hour doing, trying to find that padding function and whatnot. Actually, yeah, I'm not happy with that 0. I just want to get rid of some of this other stuff over here. I don't want any distractions. We've properly derived the number in binary, so we'll use that number now after we put the 0 on the left, and we'll think about what we're actually trying to do here. Okay, so there we go. So basically, we're trying to swap these things, right? So we're trying to take like this number and bring it over here. We're trying to bring this one over here, this one over here, and this one over here. And then we're doing the exact opposite for the other direction. So let's get another like really kind of festive color. I guess we can't do like a white, can we? No. Let's go with black then. Close enough. Okay, so then these ones want to sort of go over here in this swapping arrangement we have. So, okay, what do we get after all of this? So we get, the 1 is over here, we'd get a 0 over here, a 1 here, a 0 here. Both of these are going to be 0, and then we're going to have our 0 here and our 1 here. Okay, and that's what we expect from the other thing, right? Yeah. So that's our 133. Okay, so basically the way I want to look at this is in terms of some of our bitwise operators. Whoops, where was it? Yeah, these ones in particular, the left shift and right shift. We want to be using those over here. I think they're going to be relevant because we're basically taking like all of these numbers over here and we're left shifting them by 1, right? That's essentially it. So we're taking all of these and just doing a left shift by 1. So left shift by 1. And then we're taking all the other ones, I guess the even ones, you could say. We're taking these and we're right shifting them by 1. Whoa, okay, that turned out a little weird, but anyway, who cares? Okay, cool. So basically, yeah, that part is simple in the sense that we know how to do a left shift, we know how to do a right shift. We've got a lot of experience with those. That's no problem. But the problem is actually getting it sort of chopped up like this to the point where we would have these like red and black numbers, right? Where we would just have like the even ones and the odd ones. How are we going to handle that? Well, I can think of one way to do it. I mean, we could basically just have for the red numbers, well, okay, for both of these, we'll use what I believe they call a mask. And so basically we're going to use the AND operation with a number that's going to show us which bits we should consider significant and then turn all the other ones to 0. That's essentially it. So let me try to illustrate that. We would have something like this for the red ones. So it would alternate between 0s and 1s. The idea behind this number is that anything with a 1, because we're going to do an AND to this thing, right? So anything with a 1, it's going to remain the same, right? Because 1 and 1 is 1. 1 and 0 is 0. So anything with a 1, when we AND it, it's going to remain the same. Anything with a 0 here, well, 0 and anything is going to be 0. So anything with a 0 here is just going to turn to 0. So if we were to AND this number, our original number, with this thing right here, it would give us just the bits that we want to do the left shift on. And for the other part, we could use a really similar but kind of opposite number. In fact, I guess this would be like not this number over here. Not that it's really going to make a difference because it's not like we can store a variable in this case anyway because we have to return it in one line. But, oh well, it's good to dream big. Okay, so here we go. We've got this other number here. We want to do an AND with all these guys over here. So we could do something like that, right? So the game plan would be to take our 0, 1, 0, 1, 0, 0, 1, 0, 1 number, AND that with our original number, n, and then left shift 1. And then take this number over here, AND that with our original number, and then right shift by 1. And then with the two parts that we get from that, because we would basically get like, we'd get this part coming out of the result. And then we would also have the red part coming out of this result over here. So the idea is that these are mutually exclusive. Like they're going to occupy distinct spots. They're not going to interfere with each other. So we sort of have some leeway in terms of which operation we can use to put these together. One way we could do it would be to actually just add the two numbers because they're going to fill the slots that each other is missing, essentially, right? They're going to have the bits that each other is lacking. And so basically the idea is that we could just use a plus here. We could use an or as well. It's I guess I hesitate to use the word overkill, but like, I don't know if we totally need it. We could get away with an and. I don't know which one's better. Maybe the or is more bitwise, so maybe that's a better way to do it. But this is basically our game plan, okay? So if anyone has any questions about it, let me know. But the main point of it is that we're going to use masks. So we're going to have the odd number mask and then the even number mask. And we're going to use those to separate the two distinct parts of these. One part is going to get left shifted, the other part is going to get right shifted, and then we're going to reassemble these numbers, the results from those. We're going to reassemble them using either an or a plus. Okay, so that's the plan. We got to pull off that plan in one line, so we might as well get started. Now, what I'm going to do first of all is I'm going to do a parse int with a second argument of 2. And for the first argument, I'm going to put in basically the number we're looking for. So this one is for the odd numbers. So we'll just do this.repeat 16 times because this is going to be a 32-bit integer. We need to consider all of those. So we need to make this a 32 length string. Then we're going to convert that to a decimal number, right? We'll have a binary string. We'll convert it to a decimal number. And what we're going to get is this thing. Yeah, it's a really big number. So what is this number? This is like 1,431,655,765. Well, that is basically, well, let's take a look at what that would look like without the parse int. Maybe it makes more sense in binary. It's this. So this is our odd number mask. This is like the big version of this one that we have over here. So that's the one that we want to left shift, okay? But we need it in binary, so we can't just write it out like this because like the way this is going to be interpreted is just, well, that's a number, so like that's just a decimal number, right? This is the way you write numbers in JavaScript. It's just going to interpret it as decimal. And I thought that was always definitely going to be the case. What I didn't realize is there actually is a way to type in just a binary number, not as a string, but as a number. This, I believe, is an ES6 feature, but we can do 0 and then lowercase b, and then the binary number, we want to follow that. This is based on an older convention used for hexadecimal, and notice we get the same thing. Okay, so cool. That's pretty nice. What do we want to do with that? Well, this is basically the number that we want to do the and with our original number, n. That's the mask that we're performing on this thing. So we're basically just saying we want to only get the odd bits from this one. And then we'll also get, might as well just put this in for now. So we'll just use a plus and, oh, I've got a slick way of getting the other one. I was going to go ahead and do like the same thing, the same like generate it using the same tricks we did with the other one. But instead, check this out. Oh, real sneaky. Okay, so this would be our even number mask. And so here, let's make this a little bit bigger. We're going to shorten these maybe later, we'll see. But for now, it's going to be something like this. Now, don't forget, we want to do some shifting on these things. So with the odd numbers, we want them to shift left by 1. With the even numbers, we want these to shift right by 1. So that they basically, the bits that the other ones leave empty, these ones are going to swoop right into those spots. Okay, and I think we're ready to give this a try, and it works. Okay, so to answer the question from before, was it possible to do this without converting to a string? Yep, looks like it's possible. Okay, cool. Now, keep in mind, there are other ways that we could do this. It doesn't need to be using this binary string over here. There are other ways to do it. We can also use hexadecimal, so that's if we were to put an X here. We could use octal as well, which would be an O, but I think hex makes a little more sense here because it's like 4 bits, right? Hexadecimal is 4 bits. It's where we have, okay, if anyone's not familiar, hexadecimal is basically a number system that's base 16. And so just like a base 2 number is binary, so it just has 2 digits, 0 and 1. A base 10 number is decimal. It's a base 10 number system, so it has 10 digits, 10 different digits. 0 to 9. a hexadecimal number is base 16, so it would have 16 different digits. So it has 0 to 9 and then A to F as well. So you might have seen these, maybe if you're like working with CSS, doing colors or something like that. It's a common spot to see hexadecimal in, but it's also sort of a nice way of getting some nice compact information. I mean, there's more than that. You can use base 64 or stuff like that, but if you really want to minimize the number of bytes, like if we don't want something awkwardly long like this, then we can sort of use hexadecimal for that. Well, I shouldn't say sort of. We can totally use hexadecimal for that. Basically, the idea is we're going to take each set of 4 bits and we're going to convert them to a single character, right? Because we have 16 different characters to work with, different digits to work with. So we can handle 4 bits at a time. So what would this number be? 0, 1, 0, 1. That's the number 5. It's a 1 and a 4, so that's the number 5. So basically, we could turn this into the number 5, and then what do we get after that? Well, another 0, 1, 0, 1, so that's another 5, another 0, 1, 0, 1, so that's another 5, another 0, 1, 0, 1. So basically, we're going to have, I think, 8 of these, right? So we'll put this into hex, and it's just going to be a bunch of 5s. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so does that work? I guess we could test it right now. Yeah, it works. So that's a good way of doing it. What's the other one going to be? Well, it's 1, 0, 1, 0. So, well, what is that? That's a 2 and an 8. So that's 10. Well, that's going beyond our typical digits, right? In decimal, we don't have a digit for 10. We only have 0 to 9. But in hex, we do. We have A. So, let's see. Rainbow, you're a hex guy. Do you know, do I use capital or lowercase? Is it capital for these ones? Oh, lowercase? Oh, it is capital. Okay. Yeah, there we go. Okay, cool. So, great. I like that better, I'd say. It's nice and compact. Look, it fits. It's the first one that we have here that's not bleeding onto the other line. Look at these. This one's taking up 3 lines. That's disgusting. Anyway, point is, okay, cool. We've got these. It's working good. No problem. Yeah. And like we said before, I mean, we could do the same thing using the OR. Maybe that's more bitwise. It's up to you. Maybe we should include them both. I don't know. Maybe we'll switch them up in some way. So here, let's say that that's going to be 4, and yeah, we'll make this one the last one. And actually, okay, while we're here, we'll make that change, but let's make another change too, because remember, we did find that there were actually decimal numbers that we could use for these, and I'm just pasting in the decimal numbers that I have here pre-calculated from these. So we could put them in decimal, and it's the same number of characters. I mean, it's up to you. Like, if you're really trying to save space, it's hard to tell which one's better, right? I mean, these would have to be like longer and stuff like that for it to actually make a difference. But anyway, the point is, I think just in terms of in terms of reader clarity, I don't know if either of these are ideal, but I'd say this one's at least a little better because we can sort of see the pattern happening in these numbers. It's clear that these are repeating numbers. There's nothing about these that sort of suggests that they have this periodic nature to them. So I would say probably this one is best. In fact, maybe let's make that like the official one and make this one number 4. It's subordinate down over here. Okay, so let's run that, and great. We'll just make sure it passes all the hiddens. And there we go. Okay, cool. So let's see. Yeah, I think that's going to be it for that one. We pulled it off. I mean, this worked pretty well. I think that's a nice, I think it's an elegant solution. Oh, and see you later, Rainbow. Have a good one. Thanks for stopping by. Okay, so cool. All right. I think we're done with that one. Let's get back out of here. So, all right, great. 75% of the way.